All right. Last set of notes on gases, so that's good. And this one should be pretty short. There's really just one concept to cover here, and it is the difference between everything that we've been talking about in this entire unit and reality. So all of the equations that we've learned in this unit, all the equations we've been using, they don't really work in the real world. Having said that, they really kind of do. Just depending on the situation, they may or may not. Okay, but under normal conditions, they're a pretty good approximation. They're not exact. Okay, and in order to get the exact or more exact idea of what a real gas is doing, we have to use a different equation that's a little bit more complicated, derived using calculus. But it's not that difficult of an equation. The only reason I cover this is because the equation is on the equation sheet on the AP exam, which tells me that it could be fair game for an AP question. Now, the kind of question they're going to ask you about real gases, I don't think you will need the equation for, but I'm going to go over the equation with you and show you how to use it just in case they put something like that on the free response section. They wouldn't put it on the multiple choice section because you don't have your equation sheet, and there's no way that they expect you to remember that equation. So, anyway. Moving through this quickly, real gases are like ideal gases at high temperature and low pressure. Okay, and if you just remember the, let me see if this is on the next slide here before I say this. Okay, I guess the assumptions are sort of addressed here. If you remember when we talked about the ideal gas assumptions in a couple of note sets ago, we said that ideal gases don't take up any volume, and that they don't really have any attraction for one another. Okay, well, real gases actually do have some volume, obviously, and they really do have a little bit of attraction for one another, especially when we're talking about polar gases. Okay, and so so it's important to sort of take those things into consideration under certain conditions. Okay, and those conditions are, if we go back here, at low temperature and high pressure. Because if you think about it, if you put a gas into a small container and you really compress it and you squeeze those particles together, you put it under a lot of pressure, okay, and then you slow down the movement of the particles. You decrease its temperature quite a bit. So now these particles are moving very slowly, and they're very squeezed into this tiny little space. Then obviously our assumptions about gases start to break down. Now the individual volume of each gas molecule actually does start to matter because it's in such a small container. Now more of that empty space is being taken up by the actual gas particles. And then the other thing is, as they're moving slower and they're closer to one another, those intermolecular forces really do start to be a little bit more important, and they start influencing one another. Okay? So, those are the main things you have to understand about real gases versus ideal. Now, there are a couple of corrections we can make on the PV equals nRT equation in order to account for these things to some extent. The actual volume is going to be a little bit less than what we've been calculating because the particles do take up a little bit of that volume. Okay, so in the PV equals nRT, when we talk about a 2-liter container, really less than 2 liters of that is available for them to move around in because there's other particles in there that are taking up a little bit of that space. Okay, so it's not really 2 liters, it's a little bit less than that. The more molecules we have, the more of an effect this is going to have, and the less ideal this gas behavior becomes. And bigger molecules are going to have more effect. Okay, so this is kind of important. I think you've got a couple questions on, well, actually, I think you just have one question on 10.9 on your AP packet, but the question is, which of these gases is the least ideal? And then it gives you a list of gases. The way you're going to figure that out is just look at the molar mass of the gases. The one that's the biggest is going to be the least ideal because you put a bunch of those into a certain size container, and they're going to take up more space than any of the other particles, so they're going to be the least ideal. Okay, so our correction here, we have to subtract N times B. Okay, B is a constant that's going to differ for each particular gas, just depending on its size. Okay, and N is just the number of moles. Okay, so then to find the, let's say we're trying to calculate the pressure of this gas, and we're taking this into account. Now instead of nRT over V, which is our normal ideal gas equation, this becomes nRT over V minus NB, and that gives us a more accurate volume when we do our calculation. Okay, so that's our volume correction. Now we also have to do a pressure correction. Okay, so what happens here, because of the attraction of the gas molecules for one another, the more attracted to each other they are, the less hard they're going to hit the sides of their containers, because as they move past other gas molecules, they get attracted to them, and that slows them down a little bit. Okay? So they're not going to push on the outside of their container as much if they're being, pulled inward by their attraction to other gas particles. So actually that's going to reduce, a real gas is typically going to have a lower pressure than the ideal gas. Okay, and again, this depends on the type of molecule, and it depends on the number of molecules that we have. Okay, because again, the closer these things are to one another, the more attracted they're going to be. And then type of molecule we're talking about, is it polar, is it non-polar, because that's going to affect the intermolecular forces that are on it. Okay, so the thing with this one is we're talking about the interaction between two different molecules, so we have to square this effect. Okay. So let me talk about what these things mean. Again, N is the number of moles, V is the volume, okay? And then A is just, once again, that's a constant. It doesn't mention this on here. But A is just going to be a constant number that has to be given to you, and that A is dependent on the polarity of the molecule. I felt like that was on here. I guess not. Okay, so you put all of this stuff together, both of these corrections in here, okay? The observed pressure is going to be, you got nRT over the V minus NB, so there's your volume there, minus the correction for the pressure, okay, which is the A times N over V squared. Okay, put all that together, rearrange it a little bit, and you end up with this PV equals nRT, but the P is going to be this value here, and the V is going to be this value here. Okay. So this part is the corrected pressure. The part on the right here is the correction for the volume. Okay, and that's going to give you a little bit more accurate read on what the gas is actually doing. Okay. So, okay, here it is. See, I knew that this was on here. A and B are determined by experiment. They're going to be different for each gas, so those values will have to be given to you. If they ever gave you a problem that had to do with real gases, they would have to give you the A and the B. And really, other than the A and the B, there's nothing strange about this formula. It's just plugging in all of our pressure and volume and number of moles that we've always been doing. It's just, you're plugging it into more places, okay? And again, the only time they would ever give you this equation or this type of problem is on a free response question when you have the that equation in front of you on your equation sheet. Okay, so don't even think about memorizing this. Don't worry about that. It's not worth your time. The A and the B value, it says look them up, but again, on the AP test, you wouldn't look them up. You would, they would give you the value. And same with any test that I give you. Now, I will tell you, I'm not going to give you a question on real gases where you actually have to do a calculation. The kinds of questions I would give you would just ask about, which one of these is less ideal, or which one of these situations would make a gas be less ideal, that sort of thing. Okay. Bigger molecules have a larger B, because again, that's the correction for the volume. A is going to depend on size and polarity, okay? because that's the one that has to do with the intermolecular attractions for one another and the reduction of pressure. So those are the things that kind of factor into figuring out this B and this A. Okay, and then once those are given to you, just plug and chug. That's how you do it. So here's an example of one, just in case you ever did see a calculation like this on an AP exam. This is kind of what it would look like. Calculate the pressure exerted by 0.500 moles of Cl2 in a 1 liter container at 25 degrees Celsius. And we're going to do that first using the ideal gas law. Okay, so again, we're just doing PV equals nRT on this first part. So our pressure here, that's what we're trying to find, okay? Pressure equals, we've got the number of moles here, 0.500 times R, I'm going to run out of room, 0.08206 times our T, which is 298. Sorry, I'm going to have to put this up here. And then all of that is divided by our volume, which is 1. Okay? So then when we do that, this is, just a normal PV equals nRT problem here. We should get a pressure of, seems a bit high. Let me try that again. 0.5 times 0.08206 times 298. Okay. It's just a big pressure. 12.2, and that's in atmospheres because that's the R that I used. 12.2 atmospheres. I guess that's a lot of moles of chlorine to have in that small of a space. So there's our ideal gas. Okay. Now actually, the reason that they gave you this particular scenario is because you obviously have a lot of gas crammed into a small space. That's going to make it less ideal. Okay. So 12.2 atmospheres, that's using the ideal gas law. I'm going to write this up here so that we have that to reference when we calculate the other part. Alright, and then we're going to use van der Waals equation, and they're giving us the A and the B on this one. So then we have to go back and kind of take a look at that equation. The P part of that equation, see, I don't even remember this off the top of my head. P plus N squared A over V squared. Did I write that right? Okay. And V minus NV. Alright, so there's our equation. And I'm going to actually use all this space. Well, no, I need the A and the B. Okay, so we gotta just plug all this in. The pressure is the thing we're trying to find here. Okay, so just leave that as P for now. I'll have to do some rearranging here. N squared, so that's 0.5 squared times our A. Capital A there, it's supposed to be lowercase. 6.49 divided by V squared, which is just 1 squared. Okay. So that whole thing times V minus NV, so that's 1 minus 0.5 times our B value is 0.0562. And that is all equal to nRT, which is 0.5 times, and this A is given to us with atmospheres, so we need to keep that consistent. 0.08206 times our temperature, which again is 298. Okay, so again, then it just becomes a plug and chug. So we're going to end up with, let's see, P plus, if we calculate all this. The biggest danger on this is just making a miscalculation somewhere that screws up the whole thing. So I'm getting 1.6225 times .9719. So you can see that changed the volume just a little bit. And that's equal to, on this side, when we multiply these together, 12.23. Okay, and then you just need to distribute 0.9719 times P plus 1.576 is equal to 12.23, and then we just solve for P. So once we get all this done, then our pressure should be about 10 point, let's see how many sig figs are we using here. Looks like 4. Okay, so 10.96 ATM. Okay, so you can see there the difference in these two pressures, 12.2 versus 10.96. That's actually kind of a significant difference. So if you've got a gas that's really compressed, then that pressure actually lessens because you basically have those intermolecular forces that are acting on one another there as far as the gases, and they push on their container a little bit less hard. Okay, and then we also had a little bit of we had to take into account the fact that these particles actually have some volume. Okay, so that's it. Again, if you ever need to do a calculation with this, it's really just a plug and chug thing. They will give you A and B, and then everything else you're familiar with. It's just P and V, RT. But the main thing you need to know is that the bigger the gas, the less ideal it is, and the stronger the intermolecular forces, the less ideal the gas is going to be. And really, the way that you're going to make a gas less ideal is by putting it in a situation where it's at a low temperature, so the gas particles are moving slowly, and it's at a very, high pressure or a small volume. Okay. And those are the kinds of situations when you put the gas molecules close to one another and you slow them down, then they're going to stop acting so ideal and they're going to become more real. Now, in a room this size, the room I'm standing in, our classroom, at normal room temperature, the ideal gas laws work really well. Okay, you don't really have to worry about a correction for that. But when you compress these things, that's when you start to have to think about the reality of those intermolecular forces and the size of the molecules. Okay, if you get that, that's really what you need to know for the AP exam. Okay, and for my test. All right, that's it. See you in class.